Thank you for coming to our presentation of the SL MIPS. My name is Michael and this is my partner Liam. And today we're going to be first talking about the introductions of the MIPS and the schematics of how we built our MIPS. And also we're going to talk about the baseline instructions, which includes the R-type instructions, I-type instructions, and J-type instructions. And lastly, we're going to conclude with talking about our enhancement and what makes our processor special.
So, in introduction to our processor, we named the SL MIPS, which stands for the Senior Level Million Instruction Per Second Processor, which is based on the original MIPS processor built in the 1990s. And the reason we named it the Senior Level MIPS is because it's in the culmination of everything we've learned over the 4 years of school, from past experiences with Verilog, working with different projects, working with different processors such as the Tramwell and 460. And really, we made it our own using all the experience we had from other classes. And this processor, based on the baseline MIPS, runs a reduced instruction set computer instruction set, which means all operands come from the internal 32 by 32 register file, and all accesses to memory must be done with special operations using the store or load word. And then in our processor, pretty much been set for the enhancements, all data is processed in 32-bit signed and unsigned integer formats. So that means all registers that data is passed through intermittently, and the register file stores the data in 32 bits. And so here we have some basic block diagrams discussing how our system is made. And for all block diagrams, the ones we will be showing for now will be based on the baseline instructions. And when we get to the enhanced instructions, we will show individually what each enhancement we added to the diagram. And then here we have the basic top-level module, in which you can see the only inputs are the system clock and reset, where it instantiates the CPU, the data memory, and the I/O memory. And here we have the top level of the CPU, which includes the 3 major functional blocks, which include the instruction unit, which contains the 1K by 32 instruction memory, which is originally a 4K by 8 memory, but it is instantiated in big endian format, resulting in only 1K memory. And that is in pair with the control unit, which handles all control signals to be dealt to the data path and the instruction unit. And then the image or data path, which takes care of all data manipulation and contains a register file. And so here we have the instruction unit, which is a very simple module, which contains the program counter and the instruction register, which interface to the instruction memory. And here we have the image or data path, which contains most of our data manipulation, with a custom instantiated ALU that handles 32-bit operations, with the exception of 64-bit multiplication and division.
So the first instruction that we want to introduce is the R-type instruction, and R-type means register type instructions. And these are the instructions that has to do with data manipulations stored in the register file. And over here we displayed how the datas are formatted into the instruction. And these are just some examples of the R-type instructions. As you can see, only the registers are being used in the R-type instructions. So the blue lines indicates the inputs coming out from the control unit, and the red lines indicate the data flow during an R-type operations.
The next instruction we have is the I-type instruction. It's similar to the R-type instruction, where it has one source operand, and instead there's only one destination operand compared to the 2 source operands from the R-type instruction. And this I-type instruction contains a 16-bit immediate value, which is used to either use as an immediate value in calculation or to be used as an offset when interfacing to memories. And here we have some examples of I-type instructions, and notice all of them use the sign extended immediate value or the immediate value paired with zeros or used as an interface to memory.
Now the last baseline instruction that we want to introduce is the J-type instruction. Now the J-type instruction has to do with almost all jump instructions, but not all. One example of a jump instruction that's not a J-type instruction is the jump register instruction. So these are some examples of the J-type instruction. As you can see, this is how the address is used to calculate what the effective address is to be loaded into the program register or program counter register. So next we want to introduce our enhancements, and these are the list of enhancements that we have. We've broken it down to half-half. The first half of our enhancements are basic rotations, including the right rotate, left rotate, and jump flags. And the second half of our instructions are SIMD, which are basically vector types instructions. This includes the move general purpose register, which takes a general purpose register, moves it into the vector type, vector register file, and move VPR, and the rest will talk as we demonstrate each instructions.
And so the first enhanced instruction we're going to go over is the rotation right and rotation left instruction. And these utilize the 1F opcode that's available in baseline MIPS, however unused by any instructions, so we use it for all enhanced instructions. And this one contains 2 source operands, and then 1 destination register, and then uses the shift amount to control how many it is rotated, and then it uses our special function select of 0, 0 for left and 0, 1 for rotate right.
So this is just a rotate right explained. So initially you see the incoming data that's going to be processed through rotate right. Below displays the result that we should get. And basically what a rotate right does is it shifts all the data bits to the right by 1, or specified by the shift amount. But for the least significant bit, instead of going out of the data frame, it goes back to the most significant bit. And rotate left is almost the same as the rotate right, but instead of shifting it to the right, it shifts the data bits to the left. And instead of the least significant bit going to the most significant bit, the most significant bit will go to the least significant bit, as you can see by the arrows. So
here we have a basic diagram of how the rotate right operation occurs. It's very similar to a normal R-type operation. It uses all the same already instantiated multiplexers, registers, and everything. However, it just adds additional functionality to the already instantiated ALU to allow for the customized shifting.
So to verify this instructions, we first tried verifying the rotate right instruction. So we initially loaded 0, 1s into register 14, and we did a rotate right accounting with 3 shift amount to test our shift amount, whether or not it works. And the output result should be a 2, 0. For the rotate left, we loaded register 14 with 8, 0, and we did a rotate left with a shift amount of 3, and the value displayed should be the result that we get.
Where is the shift amount?
The shift amount is right here.
Where do we see it in the assembly language?
Oh, right here, sorry.
No, in the assembly language. That's the machine code. It just says rotate right R14, R14. In the assembly language.
No,
Oh,
you just didn't comment it.
oh, I didn't comment.
That was
Oh,
just-
okay.
Yeah, that's okay. Yeah, I didn't comment it, but that's why I'm explaining right now. So this is the image that we got from our simulation, and as you can see, the results match with the expected data in register 14. This is the result for the right rotate, and that's the result for the left rotate.
And the next operation we're going over is the jump flags. These work very similar to the branch operation. They utilize a 1F opcode, and then we have it equipped with a 20-bit jump address count offset, and that is paired with the function key reselect of 02 to 05, representing each of the 4 important flags: carry, overflow, negative, and 0.
So what's a jump count? A jump count is basically like the branch count, but instead of 16 bits, we're utilizing 20 bits to perform the count. So it takes the number of jump counts, multiplies by 4, and then adds it to the current PC counter. And as you can see, this is the branch range sign, and this is the jump range sign. It's significantly much more than a branch range.
Yeah. So it's a relative branch.
Right.
And so here we have the diagram, and for this, we actually implemented a small change. Here we have there to the right of the ALU, we implemented the register to hold the flags, while they're usually just passed through as wires to the control unit. This way, when the previous operation occurs, it will save the flag values, so we can use them for comparison in the jump flag operation.
And we did this because once you perform an add register, you have to write it back to the register file, and the FS function state doesn't depend on the previous operation. So the flags might be skewed after we get to the next operation.
Right.
That's why we have a loadable register for the flags.
Right.
So, and this is just showing the data path of how the IR is calculated for the effective address that we want to load into the PC. So to verify this, we first loaded a negative value to register 13, and we performed a jump negative. if our jump negative did not work, which it should because we loaded a negative value into register 13, then it wouldn't display all Fs in register 14. But if it did work as intended, then we loaded a pass flag, which is all Fs, into register 14. And this is the result of the verification. As you can see, register 14 is loaded with all F, asserting that our jump flags work.
And so the next operations we're going to be going over are the vector SIMD operations. And these are all 64-bit operations, and in order to use those 64-bit operands, we have a move general purpose register function, and what this does is it takes two source operands, RS and RT, from the 32-bit register file and passes them through into the vector register file, into the destination BD. This uses two source operands and one destination operand using the function code 0x06. And so we have the modifications we added onto the integer data path. And so for this, we noticed that out of the register S and register D, we concatenate the two together to create a 64-bit wire named from GPR. And that 64-bit wire is passed into our vector data path, which is similar to the integer data path with a few exceptions cut out due to the limited functionality. And this is passed into one of our two inputs into the vector register file with the assertion of the right GPR signal to imply that the written value is coming from the GPR and not being passed through from the vector data path itself. And here we have vector add saturated unsigned, which is our first vector operation. And what this does is it takes two vector source operands and one vector destination operand and performs an saturated add with the function code 0x08. Go to the next page. And the way that this works in any operation we will be going over inside the vector data path, unless it involves moving to the integer data path, all the operations will take roughly the same form, in which the S, T, and C operands, because some of the vector operands will use up to 3, they'll pass through the customized vector AOU into the Y register and back into the vector register file.
How big are those registers, S, T, and C?
They're all 64-bit.
Okay.
And for that, we have the saturated add. And the saturated add, what will happen is we will load the values into R1 through R4, pass them through into the vector register file using the move general purpose register, and then perform the saturated add function.
So just to note, this verifies our move general purpose register instructions and our vector add unsigned saturation.
Mm-hmm.
And here we have the result. As you can see, for the vector saturated add, it divides it into 8 sections of 8 bits, and then it will take each of those 8-bit sections from the two operands, add them together, and store that specific result in the desired register. And as you can see, the initial registers are correctly passed over into the vector registers, and then it is stored with the correct result into the destination register.
So our next instruction is the vector multiply and add. And what this does is basically takes vector T, vector S, multiplies them, and then adds them together to vector C,
Mm-hmm.
which later stores into the destination specified by vector D.
Mm-hmm.
So this is our steps in performing this operation. We first loaded a value from general purpose register 1 through 6, and then those values are loaded into vector purpose register 1 through 3, where we perform our operation after. And then we store the results into vector register 4. So this is just the source code that we use to compile and verify that. We loaded this into the instruction unit, and this is the result as that we got. What's displayed on my left shows the data loaded and what was performed with the arithmetic operation,
Mm-hmm.
and below shows the result. As you can see, the results that on the left matches with the results we get from the picture of the simulation on the right.
Mm-hmm.
The next one we'll be going over is a vector multiply even integer. And this is another operation that uses two source operands and one destination operand with the function code 0x08. And the way we verify that is that it takes two separate vectors that we load up from the general purpose register. It performs the desired multiplication operation, which we'll show on the next page. And so what this does is it takes the odd operands, because it's divided into groups of 8, it will take every other one, perform the desired multiplication, and then store them into the desired register. And as you can see, all 4 registers from the register file are loaded properly in, and then the correct result is displayed on our V3.
Our next operation is the vector multiply odd integer, and it's exactly like the vector multiply even integer, except of multiplying the even bytes, we multiply the odd bytes. And the verification is the same. We use the same data for it too. We loaded it into general purpose register 1 through 4 again, and then we moved that to vector purpose register 1 through 2, and then the results are stored in vector register 3. The data displayed on my left shows what the values are loaded in, and this image shows the results that we should get. And as you can see from the picture of the simulation, the data we receive from the simulation matches with the data expected, or that we wanted.
And the next one is vector merge low. This is another operation that uses 2 source operands and 1 destination operand with the opcode 0x0c. And then what this will do, it'll take the 32 bits of 2 vector operands and store them inside 1 vector. So taking 2 32 bits from both of them creates 1 64-bit vector. And the way we verified this is we simply loaded 2 of the vector operands from the register file and performed the merge low function to store the result inside V3. And as you can see here, the lower 32 bits of both operands correctly match what is placed into V3 by the operation.
Our next instruction is called the vector merge high instruction, and what it does is instead of merging the low 32-bit, we merge the high 32-bit out of the 64-bit. And also our last instruction is the move vector purpose register. So what this does is basically grabs the values in a vector register file and stores it into 2 different general purpose register files. This allows communication from the general purpose registers and the vector purpose registers. So this is how we perform the vector purpose register move. We pass it through the S register down to the vector ALU, and the vector ALU performs a pass S, just like our pass S in the normal ALU, and it gets stored in Y. Now, the tricky part is the high-low select. So we first take the low 32 bits, and passes it through, and from VPR will go into an input of the register file, which gets selected through this high-low select, coming out from the control unit into the vector integer data path.
Just to add, that occurs because we have a 64-bit vector coming out of the vector data, and you can only write 32 bits at a time on the normal register file, so we have to do it in 2 clock ticks, 1 to load the upper half and 1 to load the lower half.
So this is just showing what happens in our regular data path. So from VPR comes in from a TMUX will decide whether it takes the ALU out from the integer data path or the 32 bits from the vector integer data path. And this write VPR is the control select for that MUX to allow us to select the from VPR instead of the ALU out. So for our verification, we did a 2-1-2, just like our initial our initial 2 vector instructions. So we first merged the high value from vector 1, vector 2, taken from register 1 through 4, and stored it to vector register 3. And from vector register 3, we take the 64 bits and store them in general purpose register 5 and 6 respectively. So as you can see, this is just explaining how the vector high merge should work. And instead of concatenating the S value with the T value, it fills in every other space, as you can see from the wire. And the results to the left shows that our move from vector purpose register also worked because register 5 and 6 were filled with the same values of vector register 3. Takes the high value first, and then the low. And the arrows just displays, clarifies. So that concludes our presentation. Thank you very much.
Further questions?
Awesome.
Thank you.